All right, so we're going to start talking about thermodynamics now. And thermodynamics is really the study of systems made up of many, many particles. Okay, and so nominally what you've done in 1A and so far in 1B is considered systems that are mostly you think about point masses being acted on by forces. Now, certainly as we did problems in 1A and in 1B too, you considered extended objects. For instance, you considered a tennis ball, okay? And you imagine you throw the tennis ball and you can calculate using Newton's laws what the trajectory of the tennis ball is, how energy is shared between potential and kinetic. But in reality, there's a lot of atoms within the tennis ball. And so it's not just one object, it's a composite object. And it turns out that um, you have to take care in describing that kind of system, because not only can the tennis ball and all the atoms move together with a certain velocity, it turns out that each atom within the tennis ball can do its own thing, and it can move in different directions. But how do we deal with that? Okay, we certainly can't keep track of the velocity of every atom within the tennis ball, but it's important because the motions of the atoms within the tennis ball can actually take up energy. And a good example of this is a problem where, say, you take a tennis ball and you drop it, okay, through gravity, and you can take Newton's laws and calculate the velocity that it will have once it reaches the floor, right? But once it hits the floor, the tennis ball will deform, right? And then it will bounce back up, okay? But you can do this experiment at home. You drop a tennis ball from some height. It doesn't come back up to that same height when it bounces. You get an inelastic collision here, okay? So energy, that kind of collision, we would say the mechanical energy is not conserved. Okay, somehow energy disappeared. Now, energy is always conserved. Okay, it has to go somewhere. And in this case, the energy that you lose in the net motion of the whole object can actually go into, at least in part, there are other places it can go, but in part it goes into the internal energy of the tennis ball. And what I mean by that is the following. So each atom within the tennis ball has a velocity. And so the tennis ball moves together. So for the most part, you throw the tennis ball through the air, every atom is going to move with the velocity that you impart to it by throwing it, say big V. But each atom is bouncing around, vibrating around inside the tennis ball on its own. Okay, so there's some delta V, some little random velocity that each atom has. Okay. And so when you have the tennis ball deform when it hits the ground and bounce back up, what this does is gives energy to these random motions within the tennis ball. So this piece of the kinetic energy of the atoms inside the tennis ball can get bigger, in this case, can absorb energy. Now, on average, if I take all the atoms inside the tennis ball, and I average this over all those atoms, this delta V will average to 0. Okay, so there's no net motion due to this random velocity. It's kind of in all directions and random. So you don't see that show up in the motion of the tennis ball as a whole. Okay, but it does take up energy. Okay, so the total energy in that the tennis ball has includes now the kinetic energy. Let me just write down the kinetic energy of the tennis ball. I'm going to have 1/2 mv squared, where this is the total mass of all the atoms, and this is the mean velocity that they all move with. But then I'm going to have a term that goes like the sum over all the atoms inside the tennis ball, 1/2 m, where little m is the mass of each atom, delta V of each atom squared. Okay, and so this piece is hidden energy that the ball has, that's tied up in all these molecules vibrating around inside the tennis ball. Okay, all these atoms vibrating around. Okay, and this is really what we would call thermal energy. or internal energy. Okay. Now, the question is, how do we keep track of that? And for us, when we can sense this internal energy, and it's not like we feel the ball is buzzing in our hand when we hold it. We can't feel that, but we have a sensation of what we would call hot and cold. So if you have a cold object and feel it, the reason it feels cold to us is that the atoms inside that object are not moving around very rapidly. This energy, random energy per atom inside the object is low. Okay, so it's not moving very much. For an object that's very hot, what that means is that the this average random kinetic energy that each particle has is higher. Okay, things are bouncing around inside the tennis ball when it's hot. When it's very cold, things are not moving very much. There's not a lot of energy within this random motion. Okay, now it's not. It turns out, as I'll say later, it's not just kinetic energy that you can store internal. So in addition to each, I'll say it now, I suppose. You can think about in a solid in particular, you can think about a solid as being an atom connected by a spring to another atom. Okay, it's not really a spring, it's electrostatic forces, but you can think about, a series of atoms connected by springs. Okay, so, here, I'll complete the picture. All right, okay. And so each atom can have energy that goes like 1/2 m delta V I squared, where this is the velocity of that particular atom. But each spring can have energy too. You can have 1/2 K delta xi squared. So you can store energy both in the motion of the atoms, but also in the potential energy of the interaction between the atoms. Okay, and so there's various ways to store energy within an object that's sitting stationary, right? So a tennis ball can just sit there, so it looks like it has no net kinetic energy, but you look on the microscopic level and you see these atoms bouncing around, and on average, there's energy within their motion and in the potential energy of the interaction, okay? So there's energy stored in the ball, and again, as I said, we perceive that to be when the atoms in the ball are moving around, we perceive it to be hot. Okay, so we associate temperature with this hidden energy within the random motion of the molecules. Okay, now we can define the temperature formally as being connected to the amount of energy within each degree of freedom. Okay, let me define that. So a degree of freedom is basically how many places can you store energy. Okay, now if I take just an ideal gas, a monatomic ideal gas, there I assume there's no interaction, so the springs are gone. I just have the balls, okay, moving around. Turns out there's 3 degrees of freedom. Okay, 3 places to store energy, and what I mean by that is you have energy in the x-directed random motion, you have energy in the y-directed random motion, and in the z-directed random motion. So there's your 3 places to store, internal energy. So there's 3 degrees of freedom here, 1, 2, 3. Okay. So one way to define temperature is that you can equate the temperature T, if you write it in Kelvin, okay, to the amount of energy stored in each degree of freedom. Okay, and it turns out the proportionality is 1/2 times the Boltzmann constant, which I'll can give you the number for later, and the temperature, now in degrees Kelvin, of an object. So in every degree of freedom, you're going to have this much energy. It turns out this is an energy in joules. Okay, and so each degree of freedom will have it. So for example, m delta Vx squared, okay, will be equal to, on average, okay, so I can take an average of this over time and over particles, and on average I'm going to have that much energy. That's how we can define a temperature, okay? And so each possible degree of freedom, so what we're saying is that the random energy in the x direction has energy on average that's equal to 1/2 kT, And the same is true in equilibrium of all possible places you can store energy internally. So if you have an ideal gas, again, that's just the three dimensions you can move, x, y, z. But if you're in a solid, you're going to store, on average, energy in the stretch of the spring or in the interaction forces. That's also equal to 1/2 kT. And that's because we argue the object is in equilibrium. That's if the object is in equilibrium. So, for example, if I take the tennis ball and I sit it outside and let it come to the same temperature as the outside room. And that happens by heat transfer between the tennis ball and the air around it. And what's really happening is the molecules in the air that are vibrating around are hitting the tennis ball and transferring energy to it. And eventually what happens within the tennis ball is that energy that's given to it by the outside will be transferred to every atom within the tennis ball. And so that on average, again, not every atom is moving within the tennis ball at all points in time, but on average, there's that much kinetic energy in each atom's motion in three directions and in the the effective springs that are connecting all the atoms. Okay, so you spread that energy out in that way. Okay, maybe one last concept to relay, and that is the idea of a temperature scale. So when I write down 1/2 kBT is the average energy, what I'm using is the Kelvin scale. So that's the absolute temperature scale. And so 0 degrees, or 0 Kelvin, it's not degrees, 0 Kelvin indicates that there is no energy on average in motion of the particles or in the stretch of the spring. So everything is sitting absolutely still. So absolute 0 means all the particles in the object are sitting stationary. The springs that connect them, not real springs, but the interaction energy, they're sitting unstretched. Okay, so there's no energy. And so as I start to add thermal energy to the system, that temperature will go up, and that will characterize, again, how much energy is stored within each of the degrees of freedom that this object has. Okay, so maybe with that, I'll stop here and I'll start the next concept in the next video.